So imagine walking up to like a weathered stone monument, sitting alone in a lush green field somewhere out in the Irish countryside.
Oh, right, like a traditional Celtic cross.
Exactly. You're looking at this traditional cross, and it has that iconic ring connecting the four arms, right? Carved by ancient monks centuries, maybe even over a millennium ago.
Yeah, those are incredible.
And you just trace the geometry with your eyes, the perfectly proportioned squares, the concentric circles, the symmetry of the whole design.
It's a really powerful image.
It is. But now imagine someone tapping you on the shoulder right then and telling you that the exact mathematical geometry used to draw that ancient stone cross can flawlessly predict the physical location of the dwarf planet Pluto.
Wait, really? Pluto?
Yeah, nearly 4 billion miles away in the freezing dark of space.
I mean, that is the kind of premise that instinctively makes a person skeptical, right?
Oh, totally.
Because we are taught to separate human cultural artifacts from the cold, hard, unfeeling mechanics of astrophysics. They belong in totally different categories of human knowledge.
Right, exactly. And yet, that collision of ancient geometry and modern orbital mechanics is exactly what we are jumping into today. So welcome to the deep dive.
Glad to be here for this one. It's a wild ride.
It really is. Every time we take a stack of fascinating bleeding-edge research, along with all the necessary historical context, and we extract the most profound insights just for you. But today's mission, it feels less like a standard review of scientific literature and more like, I don't know, an astronomical detective story.
Yeah, that's a great way to put it.
We are unpacking a 2026 preprint by an independent UK researcher named Salah Eddin Gerby. The paper is titled The Harmonic Architecture of the Solar System. And the core idea here is going to fundamentally change how you perceive the night sky.
It's definitely a paradigm shifter.
Like, what if the layout of our solar system, the spacing between Mercury, Venus, Earth, Mars, and all the giants all the way out to the Kuiper Belt.
Right.
What if it isn't just a random assortment of rocks that happen to stop moving where they did? What if instead the entire system is locked into a highly ordered, incredibly strict mathematical masterpiece?
And the tension here, is between what we observe through the lens of modern astrophysics and what this specific mathematical model is actually proposing.
Right, because the current view is pretty messy, isn't it?
Oh, absolutely. Currently, the scientific consensus describes planetary formation as an inherently chaotic process. You start with a primordial, spinning disk of gas and dust surrounding a young star.
Just a giant, swirling cloud of debris.
Exactly. And particles collide, they clump together, they form planetesimals, and eventually planets. But those planets don't just stay put.
Right, they move around.
Yeah, they migrate, they get pushed and pulled by the gravity of the disk, and they scatter off of one another in this, violent, messy, unpredictable, cosmic billiard game.
So it's basically a completely chaotic construction site. And you look at the final house and assume the rooms are just where the builders happen to drop the bricks.
That is the standard assumption, yeah. But Gerby's paper is pointing out, a ghost in the machine. He proposes that layered perfectly over all that historical chaos, there is a precise, quantized mathematical sequence.
So finding a pattern like this, it doesn't just overwrite the violent history of how the planets formed, does it?
No, not at all. Rather, it offers a radical new perspective on how that chaos eventually resolves. It suggests that out of infinite chaotic possibilities, gravity forces the system to settle into a very specific, deeply elegant geometric architecture.
Wow. So we are going to explore this hidden blueprint today, which Gerby calls the Silver Ratio Harmonic Framework, or the SRHF for short.
Right, the SRHF.
We'll look at how that specific Celtic cross shape generates a unique number that seems to dictate our cosmic neighborhood. We'll also look at how this math predicts a literal missing ghost planet sitting right now between Mars and Jupiter.
That's my favorite part of the paper, honestly.
It's so cool. And we will ask the biggest question. Is the universe secretly a giant math nerd? But to really appreciate how groundbreaking this paper is, we have to recognize that the urge to find a law for planetary spacing is not a new obsession. Right?
Oh, not even close. Astronomers have been bashing their heads against this wall for hundreds of years.
Yeah. So let's talk about the historical context, because that's absolutely essential here.
Definitely. To understand the significance of a model that actually works, you have to understand the brilliant, spectacular failures of the past.
Right. So if we rewind the clock to the early 17th century, we run right into Johannes Kepler.
Ah, Kepler.
The year is 1619, and he publishes this monumental work called Harmonicis Mundi, which translates to The Harmony of the World. And Kepler, he was a man standing with one foot in the mysticism of the past and one foot in the rigorous science of the future.
Yeah, it's a very accurate description of him. He was utterly convinced that the universe was the product of a rational creator who employed divine geometric perfection.
Just to anchor this for a second for you listening, this is the same Johannes Kepler who literally wrote the laws of planetary motion, right?
It was very same.
Like the laws that NASA still relies on today to send probes to Mars. He wasn't some fringe thinker.
Oh, no. He is one of the foundational pillars of modern astronomy. I mean, he figured out that planets move in ellipses, not perfect circles, and he figured out how their speed changes as they get closer to the sun.
Right.
But before he locked down those mechanical laws, his grand consuming passion was figuring out why the planets were spaced the way they were.
And at the time, they only knew of 6 planets, right?
Exactly. Mercury, Venus, Earth, Mars, Jupiter, and Saturn. So Kepler looked at the gaps between them and decided the answer had to lie in platonic solids.
Okay, the platonic solids, let's break that down. Those are the specific 3D shapes where every face is the exact same regular polygon and every corner looks exactly the same.
Correct. In all of geometry, there are only 5 of these perfect regular 3D shapes.
Okay, what are they?
Well, you have the tetrahedron, which is made of 4 triangles, the cube made of 6 squares, the octahedron made of 8 triangles, the dodecahedron, 12 pentagons, and the icosahedron, which is 20 triangles.
Okay, so 5 shapes.
Right. And because there were exactly 5 perfect shapes and exactly 5 gaps between the 6 known planets, Kepler thought he had decoded the mind of God.
Oh, wow.
He proposed a model where if you took the sphere of Saturn's orbit and nested a cube inside it, the sphere that perfectly fit inside that cube would be Jupiter's orbit.
Wait, like nesting dolls.
Exactly like that. Then you nest a tetrahedron inside Jupiter's sphere to get Mars, and so on, nesting these distinct geometric blocks all the way down to Mercury.
I mean, it sounds incredibly poetic. The cosmos built like a set of beautiful, nested geometric nesting dolls. I can totally see why a mathematician in the 1600s would fall in love with that idea.
Oh, it is arguably one of the most beautiful scientific theories ever proposed, but it possessed a fatal flaw.
The reality check.
Yeah. When you take away the romance and actually crunch the orbital numbers, it just doesn't hold up. When you measure Kepler's polyhedral model against modern, precise orbital data, it has a mean error rate of over 10%.
And 10% is a lot in space.
It's massive. In the vast distances of space, a 10% error means your model is off by 10 or hundreds of millions of miles.
Right. Not exactly a tight fit.
No. Furthermore, the model was mathematically rigid. It had a hard cap. It only had room for 6 planets.
Oh, because there are only 5 shapes.
Exactly. So when William Herschel discovered Uranus in 1781, Kepler's beautiful geometric universe shattered. There were literally no more platonic solids left to hold the new planet.
That's a classic trap, isn't it? He took a top-down philosophical ideal like the universe must be made of perfect 3D shapes and tried to force the physical data into that box.
Yeah, exactly. When you squint, it sort of works, but under a microscope, it completely falls apart.
So Kepler's nesting dolls are out.
Yeah.
But the desire to find a pattern didn't die with his theory, right? We jump forward a bit to the late 1700s, and we get an entirely different approach. The Titius-Bode law.
Right, and the Titius-Bode law represents the opposite end of the scientific spectrum from Kepler.
How so?
Well, where Kepler was obsessed with geometric philosophy, Johann Titius and Johann Bode were purely focused on numbers. In 1766, Titius noticed a curious mathematical sequence, and Bode later popularized it.
So they weren't looking for perfect shapes.
Not at all. They didn't have a grand theory. They just looked at the raw, empirical distances of the planets from the sun and noticed a pattern that seemed to fit a really simple arithmetic rule.
Okay, so how did the rule actually work? It was just a sequence of numbers.
A very simple sequence, yeah. You
Yeah.
start with 0, then 3, then you double it to get 6, 12, 24, 48, and so on.
Okay, basic enough.
Then to each of those numbers, you add 4. Finally, you divide the result by 10. And if you do this, the resulting numbers magically align with the distances of the planets in astronomical units.
Okay, let's pause. Astronomical units. So Earth is 1 astronomical unit, 1 AU.
Right. And if you run the Titius-Bode math for Earth's position in the sequence, the number you get is exactly 1.0.
Oh, wow.
For Venus, the math gives you 0.7. The actual orbit is 0.72. For Mars, the math gives 1.6. The actual is 1.52. For Jupiter, it gives 5.2. The actual is 5.2.
It is remarkably close.
It really was. For the inner solar system, this empirical sequence had a remarkably low error rate, hovering right around 2.5%.
And didn't this law have a massive moment of triumph?
Yeah.
Because I remember reading that the math predicted a planet where we didn't think one existed.
Yes. That was the moment that turned the Titius-Bode law from a mathematical curiosity into an accepted scientific paradigm, at least for a few decades.
What happened?
Well, in their sequence, there was a glaring gap at the number 2.8. The math demanded a planet sitting right between Mars and Jupiter. Bode urged astronomers to search that exact region of space.
Just going off the math.
Purely off the math. And in 1801, Giuseppe Piazzi discovered Ceres sitting at 2.77 AU. It was a stunning vindication. The math said, look here, they looked, and they found a world.
Ceres, which we now know is the largest object in the asteroid belt. So they find Ceres, everyone pops champagne, and they assume they've cracked the code of the universe.
They did, but their confidence was entirely misplaced.
Let me guess. It felt
Spectacularly. The Titius-Bode law was a house of cards waiting for a strong breeze, because it was fundamentally an empirical exercise.
meaning it was just a pattern retrofitted to match existing data points.
Exactly. It had no physical or geometric mechanism anchoring it to reality. It was just curve fitting. If you just draw a line that connects the dots you currently see, you will almost certainly draw the wrong line for the dots you haven't discovered yet.
And the dot they hadn't discovered yet was Neptune.
Precisely. When Neptune was discovered in 1846, it completely broke the sequence.
How far off was it?
Well, the Bode law predicted a planet at 38.8 AU. Neptune is actually sitting at roughly 30 AU. Yeah. The law was off by nearly 1 billion miles. And when Pluto was discovered later, the law failed even more spectacularly. Titius-Bode was abandoned. It became a cautionary tale about seeing patterns in random noise.
Let's pause and reflect on this because it sets up the rest of our discussion perfectly. Kepler failed because his geometry had no physical basis. Titius-Bode failed because their numerical sequence had no underlying geometry. They were just playing with numbers.
That's a great summary.
Which brings me back to the question of modern astrophysics. If you take an Astronomy 101 class today, they teach you about chaotic accretion.
Right.
They teach you that planetary orbits are the result of billions of years of gravitational tug-of-war, giant impacts, and messy migrations. If that's true, why are we even entertaining the idea of a neat mathematical blueprint? Shouldn't a chaotic, violent process just produce a random, scattered mess of planets?
It is a totally counterintuitive concept. But the answer to your question lies deep in the physics of something called orbital resonance.
Orbital resonance, okay.
To understand this, we have to look at the groundbreaking numerical integrations performed by astronomers like Jacques Lascar in the 1980s and 90s. Using supercomputers, they mapped the long-term gravitational interactions of the solar system over millions and billions of years.
And what did they find?
What they found is that chaotic zones and highly stable resonant structures constantly coexist.
Okay, break down resonance structures for me. How does chaos actually create structure?
Think about the concept of pushing a child on a playground swing.
Okay.
If you walk up to the swing and just push the child at totally random, chaotic intervals.
Like sometimes when they're swinging toward you, sometimes when they're swinging away.
Right, exactly. The motion of the swing becomes jerky, erratic, and unstable. That is the chaotic scattering phase of planetary formation. Gravity is pulling in random directions.
Got it.
But if you time your pushes perfectly, pushing only when the swing reaches the exact peak of its arc, you have hit a resonance. The energy transfers efficiently. The swinging becomes incredibly smooth, predictable, and stable over a long period.
Oh, I see. So gravity is the person pushing the swing.
Yes. Gravity is a relentless editor. Over hundreds of millions of years, the gravitational pulls between the planets act to destabilize certain random orbits and stabilize others that fall into these mathematical rhythms.
So the bad orbits get weeded out.
Exactly. If a planetary body is in a bad spot, the repetitive tugs from a giant like Jupiter will eventually stretch its orbit until it crashes into the sun or gets violently ejected into deep space. But if a planet settles into a specific mathematically resonant orbit, those same gravitational tugs balance out. They cancel each other's extremes.
I'm picturing a massive landscape with like steep hills and deep bowl-shaped valleys.
Okay, I like where this is going.
The early planets are like boulders dropped onto the hills. The chaotic migration, the random pulling and pushing as the boulders rolling down the slopes, bouncing off each other.
Yes.
But eventually they have to come to rest. And the only places they can permanently rest are at the very bottom of those deep valleys.
That is an excellent physical analogy. The valleys are the resonant attractors. The system naturally, mindlessly seeks an efficient, stable state of lowest energy variance.
Okay, that makes sense.
So, when Gerby's paper talks about finding a mathematical pattern, he isn't saying the planets miraculously spawned on those exact geometric lines. He's saying that this specific mathematical framework defines the location of the deep valleys.
Right. So the math isn't the invisible hand placing the planets. The math is the blueprint of the landscape where they eventually have to go to sleep.
Exactly.
But to map that landscape, to find a model that actually works for the whole system from the blistering heat of Mercury to the frozen edge of Pluto, we have to throw away Kepler's nested 3D blocks.
Long gone.
And we have to throw away the arbitrary curve fitting of Tish's bode. We need a mathematical model that is both geometrically anchored and dynamically stable.
Which brings us finally to the core of Gerby's 2026 paper.
Yes, the geometry of the Celtic Cross and the mystery of the silver ratio.
We are turning to a very specific, surprising geometric construction and the unique irrational number it produces.
Okay, let's tackle the silver ratio first.
Yeah.
Because everyone and their mother has heard of the golden ratio, right?
Oh, sure.
It's roughly 1.618. You see it in the spiral of nautilus shells, the arrangement of seeds in a sunflower, the proportions of Da Vinci's Vitruvian Man. It's famous.
Very famous.
But Gerby builds his entire planetary framework on the silver ratio. What is the difference?
Well, mathematically, the silver ratio, which is denoted in the paper by the Greek letter delta with a subscript s, is an irrational number. Its exact value is 1 plus the square root of 2.
Okay, 1 plus the square root of 2.
Right. If you were to write it out as a decimal, it's approximately 2.414, and the decimals go on forever without repeating. Like the golden ratio, it appears in various fields of mathematics, particularly in geometric proportions and something called continued fractions.
Okay, let's define continued fractions briefly, just so we don't leave anyone behind. What are those?
A continued fraction is a way of writing a number as a fraction within a fraction within a fraction, extending downward infinitely.
Like a fractal fraction.
Kind of, yeah. In number theory, the numbers that have the simplest, most repetitive continued fractions are actually the most irrational numbers.
That sounds like an oxymoron. Simple, but most irrational.
I know, it's weird. But it means they are the hardest to approximate with a simple normal fraction like 34 or 58. The golden ratio is the most irrational number of all, and the silver ratio is closely related to it in this property.
And why does that matter for planets?
Because they are so hard to approximate with simple ratios, systems governed by these numbers tend to be incredibly resistant to destabilizing resonances.
Ah. Meaning if a planet's orbit is governed by a number like the silver ratio, it's sitting in an incredibly deep, safe valley. It's mathematically shielded from being bumped out of place by the gravity of its neighbors.
That is the dynamic implication, yes. But what makes Gerby's approach so compelling is how he arrives at the silver ratio in the first place.
Right. He doesn't just pull 2.414 out of thin air and say, let's multiply the planets by this.
No, he derives his entire foundational mathematics purely from a simple, ancient geometric construction.
Okay, I am looking at figure 1 in the paper, and I want to paint a clear mental picture for everyone listening.
Go for it.
Imagine a perfect square. Now divide that square into a grid, like a standard tic-tac-toe board. You have a larger square made up of 9 equal smaller squares, a 3x3 grid.
Yep.
Now inside that grid, you take a compass and you draw a series of perfectly concentric circles radiating from the dead center. Finally, you draw a regular octagon, an 8-sided shape, like a stop sign, that perfectly touches the outer boundary of the outermost circle.
It is an incredibly elementary geometric setup.
Right.
Squares, circles, an octagon. You can draw it with a straight edge and a compass in a few minutes.
Right.
But from the very specific proportions of this arrangement, Gerby extracts 4 distinct mathematical constants, which he labels A, B, C, and D.
And as we mentioned at the very beginning of the deep dive, when you look at this completed drawing, the 3x3 grid with the circles perfectly proportioned inside the squares, you aren't just looking at abstract math.
No, you're not.
You are staring at the exact geometric schematic of a traditional Celtic cross, the ringed stone cross.
The visual parallel is striking and undeniable. The paper explicitly notes that these constants emerge directly from this Celtic cross geometry. Let's look at how the math falls out of the shapes.
Okay.
If we assign the side of one of those small grid squares a length of exactly 1 unit, we can measure the rest of the figure. The inscribed regular octagon has a specific property called an inradius.
The inradius, what is that?
It's just the radius of the largest circle that can fit perfectly inside it. Based on this 3x3 grid, that inradius is exactly equal to 1 plus the square root of 2.
Which is 2.414, the silver ratio.
Exactly. That becomes constant B. Constant A is derived as simply the square root of 2. Constant C is 2 times the square root of 2 minus 1. And constant D is the square root of 2 minus 1.
Okay, lots of square root of 2's going on.
Right. These 4 constants, entirely generated by the overlapping lines of the cross geometry, form something called a quadratic field.
Okay, quadratic field sounds intimidating. Can we translate that?
Sure. Think of a quadratic field like a specific musical scale.
Okay.
If you are playing a song in the key of C major, you can only use certain notes. You can't just mash any key on the piano. You have to stay within the mathematical boundaries of that scale for the music to sound right.
That makes sense.
A quadratic field based on the square root of 2 is a mathematical key. It means that any number generated within this framework must be some combination of rational numbers and the square root of 2. It restricts the possibilities. It creates a closed, highly structured mathematical environment.
So Gerby takes this mathematical environment, this musical scale generated by the Celtic Cross, and he uses it as the engine for his entire planetary model.
He does.
But I have to play the skeptic here, because when you say it out loud, it borders on the mystical.
I know, it really does.
We are suggesting that the geometry of a cultural, religious symbol, a standing stone carved by human hands, dictates the orbits of unimaginable masses of rock and gas billions of miles away.
Right.
It feels like saying the structural blueprint for the Empire State Building perfectly predicts the exact spacing of leaves on a fern growing in the Amazon rainforest. The two things shouldn't have anything to do with each other.
It is a completely healthy, necessary reaction to be skeptical of that parallel, and we must be crystal clear about what the research is actually claiming.
Okay, clarify it for us.
Gerby is not suggesting a causal relationship. The Celtic Cross doesn't control the planets. There is no mystical energy beam connecting a stone in Ireland to the planet Jupiter.
So what is he proposing?
What he is proposing is a case of extreme mathematical convergent evolution.
Convergent evolution. Like how sharks and dolphins both evolved dorsal fins because it's the most efficient shape for moving through water, even though one is a fish and one is a mammal.
That is the perfect analogy. The fundamental geometry behind the Celtic Cross, the specific interaction of a 3x3 grid and concentric circles, represents a state of incredible mathematical elegance and stability.
Okay.
It naturally generates these rational functions of the square root of 2. When ancient builders were designing their monuments, they likely stumbled upon this geometry because humans are naturally drawn to symmetry, proportion, and visual balance. They found the most efficient shape for their art.
And meanwhile, out in the void of space.
Out in space, billions of years of gravity, collisions, and orbital migrations were mindlessly grinding away, searching for their own most efficient shape.
Right.
The planetary system had to settle into the most stable, energy-efficient configuration possible to avoid destroying itself. And the landscape of physics dictates that the most stable mathematical valley available happens to be that exact same quadratic field generated by the silver ratio. Gravity and human aesthetics both converged on the exact same mathematical truth.
Man, that reframing makes it so much more profound. It's not magic, it's the universal language of structure.
Exactly.
So how does the model actually build the solar system from this geometry?
Well, the beauty of the silver ratio harmonic framework is its simplicity. To construct the model, Gerby anchors the entire thing to a single, undeniable physical reality: Earth.
Just Earth.
Just Earth. He takes Earth orbit as the fundamental baseline. The distance from the Earth to the Sun is defined as 1 astronomical unit. Using absolutely nothing but Earth's 1 AU as the starting point, the distance of every single other planet is calculated using basic algebraic fractions of that silver ratio generated by the cross.
Wait. You take Earth, just Earth,
Yeah.
and you plug the number 2.414 into some basic fractions, and it spits out the distance to Saturn.
That is precisely what the equations in the paper demonstrate. There is no curve fitting. There are no arbitrary constants invented just to make the math work.
Let's hear an example.
Let's look at the equation for Jupiter, for instance. The paper shows that Jupiter's orbit is calculated by taking Earth's 1 AU baseline and multiplying it by a specific polynomial function of the silver ratio.
Which is?
It's 2 times the silver ratio minus 1 times 2 times the silver ratio minus 3. You plug 2.414 into that simple algebraic formula, and it gives you the predicted orbital radius of Jupiter.
It's beautiful on paper, but theory and elegant geometry are cheap in the grand scheme of science.
Very true.
The graveyard of astronomy is full of beautiful theories that fail the test of reality. I mean, just ask Johannes Kepler. The only thing that matters is the cold, hard data. How does this mathematical key actually perform when you hold it up against the physical universe we live in?
This is the moment the paper transitions from a fascinating geometric curiosity into a rigorous, heavy-hitting analytical model.
Okay.
Section 3 of the preprint is entirely dedicated to the empirical performance of the SRHF. And the results are, without exaggeration, astonishing. The model doesn't just look at the inner rocky planets. It covers all 9 major orbital bodies, spanning the entire breadth of the system from Mercury out to the dwarf planet Pluto.
Let's talk about the error rate, because this is the metric that destroyed all previous historical attempts. What is the margin of error here?
Across that entire massive span of the solar system, the model achieves a mean absolute percentage error, the MAPE, of exactly 0.72%.
Less than 0.75% error, on average.
Yeah.
Across distances measuring in the billions of miles.
Yes. To look at it another way, the root mean square error, which measures the absolute physical distance the model is off the mark, is an incredibly tiny 0.11 astronomical units.
Wow.
We need to put that in historical perspective. Remember, the celebrated Titius-Bode law had an error of about 2.5%, and that was only for the inner planets before it completely broke down.
Right.
Kepler's polyhedrons had a 10.3% error. Gerbi's silver ratio model beats the classic historical laws by a full order of magnitude, and it does it across the entire system.
I want to actually walk through some of these numbers, planet by planet, from the data tables in the paper, because hearing the raw data spoken out loud really hammers home how wild this is. So we start with Earth. Earth is our anchor, exactly 1.0000 AU. The model works outward. For Mars, the silver ratio math predicts an orbit of 1.547 AU. In reality, modern telemetry tells us Mars orbits at 1.524 AU. That is a tiny deviation of just 1.48%.
It is incredibly tight. And as we move past the inner rocky world and cross the asteroid belt to the gas giants, the precision actually improves.
It gets better.
It gets better. Let's look at Jupiter. The algebraic prediction based on the cross geometry says Jupiter should sit at 5.172 AU. The observed physical reality of Jupiter is 5.204 AU. That is a deviation of -0.62%.
Okay, but this is the real test. What about the ice giants, Uranus and Neptune?
The problem children.
Exactly. These are the planets that completely shattered the Titius-Bode law. They are the historical graveyard of mathematical theories.
Well, SRHF handles them flawlessly. For Uranus, the mathematical prediction is 18.912 AU. The observed reality is 19.185 AU. But Neptune is the true showstopper. Neptune, the great destroyer of empirical laws, is predicted by the silver ratio to be orbiting at 30.142 astronomical units. Its actual observed distance is 30.156 AU.
Wait, what's the difference there?
That is a difference of 0.05%. The prediction and the reality are virtually indistinguishable.
That is staggering. A 0.05% difference at a distance of nearly 3 billion miles.
It's hard to even comprehend.
It doesn't stop there. It scales all the way out to the edge of the classical system, to Pluto. The math predicts Pluto at 39.598 AU, and the reality is 39.482 AU. An error of just 0.29%.
Incredible.
When you look at the graphs in the paper, specifically figure 7b, which plots the logarithmic scale validation, it's mind-bending. You have this massive spectrum from the scorching tight orbit of Mercury all the way out to the frozen dark edge of Pluto.
Yeah, that covers 4 orders of magnitude in radial distance.
And yet the ratio of the observed distance to the predicted distance is a flat, straight line hovering right at a value of 1.
That specific graph is perhaps the strongest piece of evidence for the structural integrity of the model.
Why is that?
Because there is no drift. In a flawed model, the errors compound. If your foundational assumption is slightly wrong, you might be close on the first few planets, but by the time you extrapolate out to Pluto, your error multiplies and the line drifts wildly off course.
Like drawing a line slightly off angle. By the time it goes a mile, it's way off target.
Exactly. The fact that the SRHF maintains a flat line across billions of miles indicates that it has captured a genuine underlying structural mechanic of the system.
But the skeptic in me, the voice of the statistician, has to ask, could this just be the most unbelievable cosmic coincidence of all time? If you play with numbers long enough, eventually you'll find an equation that fits your data, right?
The paper anticipates that exact skepticism. In the statistical analysis section, Gerbi provides a rough calculation to address the probability of this being a random fluke.
And what's the math on that?
Well, if you treat each of the 10 planetary matches as a separate, independent event, and you set a strict success window, say the prediction must fall within a plus or minus 2% range of the actual planet, The probability of generating this sequence by pure random chance is staggering. Gerby calculates the upper bound probability at approximately 10 to the negative 13th.
10 to the negative 13th power.
Yeah.
For anyone trying to visualize that, you write a decimal point followed by 12 zeros and then a 1.
It is essentially zero. Now, any rigorous statistician will tell you that planets aren't perfectly independent events. I mean, their orbits affect each other, so a more complex statistical analysis is needed for a final definitive probability.
Sure.
But the sheer magnitude of that number, 10 to the negative 13th, makes a nearly unassailable case. We are not looking at a statistical fluke, we're looking at physical architecture.
Beating the historical models by an order of magnitude across the entire solar system is a massive leap for astrophysics. But there is a catch.
Yes, the catch.
As I was combing through the actual equations that build this sequence, specifically equations 11 through 20 in the paper, I noticed a very distinct gap. The silver ratio math generates a perfect logical step on the ladder between Mars and Jupiter.
Right.
But when we look through our telescopes, there is no major planet sitting on that step.
You have found the empty chair at the solar system's dinner table. And this gap leads us to the absolute most fascinating and arguably the most important prediction of the entire manuscript.
Yeah.
The mystery of Harmonia.
Let's define the stakes here. In any branch of science, backward compatibility is great. If you can build a math equation that explains data we already have, like the locations of planets we already know about, that's nice.
It's good, but it's not everything.
Right. Because forward prediction is the gold standard. A theory only becomes truly powerful when it points to something we haven't seen yet and says, go look there, you will find something new.
Exactly. The silver ratio sequence explicitly demands that a planetary body must exist at a distance of exactly 2.14 astronomical units from the sun to make the math work. The framework collapses without it.
So the math requires it to be there.
Yes. Gerby names this theoretical missing node Harmonia.
Harmonia, where exactly does this invisible world sit?
Well, a distance of 2.14 AU places it right inside the inner boundary of the main asteroid belt. It's sitting in the dark space just past the orbit of Mars, but well before you reach the massive gravitational domain of Jupiter, or even Ceres, the dwarf planet we talked about earlier.
Okay, so just past Mars.
Right. And in the context of the mathematical framework, Harmonia isn't just another rock. It serves as the critical harmonic boundary. It is the dividing line between the dense, rocky, interterrestrial planets and the massive, gaseous outer giants. It is the transition point of the cosmos.
I want to spend some real time unpacking the math of this specific node because the paper dedicates a tremendous amount of analysis to it. Specifically, Gerby introduces a concept he calls the harmonic basin. Can you explain what that is and how he maps it?
To understand the profound importance of the Harmonia node, we have to look at the error landscape of the entire solar system. Imagine a massive graph.
Okay, visualizing a graph.
The horizontal axis on the bottom represents different hypothetical distances where this missing planet could theoretically sit. Maybe it's at 2.0 AU, maybe it's at 2.5 AU.
Got it.
The vertical axis on the side represents the total error of the entire planetary model. If I put the missing planet at 2.0 AU, how badly does it mess up the mathematical predictions for Earth or Jupiter or Saturn?
So you take this theoretical planet, Harmonia, and you slide its distance back and forth on a supercomputer, and you watch how the error rate of the whole solar system responds.
Yes. And what the graph reveals is a breathtaking curve. As you slide the hypothetical planet toward 2.14 AU, the total error of the solar system model plunges downward, creating a deep valley on the graph.
Okay.
The point of absolute minimal variance, the very bottom of that valley, where the entire system-wide framework fits together with the tightest, most perfect precision, occurs when you place the Harmonia orbit at precisely 2.1437 AU.
The bottom of the valley. Most stable configuration possible for the solar system.
Yes. But here is where the math goes from being merely interesting to genuinely spooky.
Spooky. How so?
Because at this exact spot, right at the bottom of that valley, three completely different mathematical concepts converge. First, you have Gerby's algebraic prediction, the number generated entirely by the geometry of the Celtic Cross and the silver ratio. That puts the node at roughly 2.142 AU.
Okay, that's one.
Second, you have the empirical optimum we just discussed, the supercomputer sliding the planet until the error hits rock bottom at 2.1437 AU.
So the ancient geometry and the modern supercomputer agree almost perfectly. What is the third concept?
The third is a purely transcendental mathematical solution, pi squared divided by 3.
Wait, pi squared divided by 3. Where on earth does pi come from in this? We
Yeah.
haven't talked about pi at all.
We haven't, and that's why it's so significant. In mathematics, numbers belong to different families. The constants derived from the Celtic Cross, the square root of 2, are algebraic numbers. They are the solutions to simple polynomial equations.
Right.
But pi is a transcendental number. It transcends basic algebra. It is fundamentally linked to the geometry of continuous circles and spheres, not rigid grids.
Okay.
If you take pi squared divided by 3, the value is roughly 3.289. But when Gerby scales that transcendental value into the specific harmonic framework of his model, it translates to an orbital radius of 2.145 AU.
Let me make sure I'm fully grasping the weight of this. You have a number generated by a rigid 3x3 grid. You have a number generated by minimizing the orbital errors of actual physical planets. And you have a number generated by the transcendental properties of a circle. 3 entirely different branches of math and physics. And they all point to the exact same spot in space, 2.14 AU, converging to within 0.07% of each other.
It is the mathematical equivalent of finding 3 different treasure maps drawn by 3 different civilizations in 3 different languages, using 3 different navigation systems, and discovering that all 3 maps place the X on the exact same single grain of sand on the beach.
That is insane.
It strongly indicates a region of immense underlying mathematical stability. Gerby charts this using an index called the Harmonic Spread Index, which measures the symmetry of the errors. Right around 2.14 AU, there is a flat plateau on the graph, a true harmonic basin. Within this incredibly narrow region, the silver ratio ladder is perfectly symmetric. The system is in perfect balance.
I am picturing the solar system as a massive, impossibly complex mobile hanging above a crib. You have these huge, heavy gas giants spinning on the outside. You have these dense little rocky planets zipping around on the inside.
Yeah, that's a good visual.
If you want to hang that mobile so it doesn't immediately tilt, tangle, and crash to the floor, there has to be a specific, mathematically perfect fulcrum point where you tie the string. It feels like the Harmonia node is that fulcrum. It's the exact point where the inner and outer weights perfectly offset each other.
That is a brilliant way to visualize it. And the raw data actually supports that idea of a physical fulcrum. In his analysis, Gerby discusses a phenomenon he calls the Neptune inversion.
I was actually staring at the chart for this, figure 5 in the paper. It plots the residuals, which is the difference between where the math predicts a planet should be and where it actually is on a logarithmic scale.
What did you notice?
I was looking at the trend line, and it does something really strange. For the inner planets, the error trend points one way. But right when you cross that 2.14 AU mark, the line just flips upside down. The error trend for the outer planets goes in the exact opposite direction.
All right.
It's almost like that specific spot acts as an anchor, keeping the outer planets from drifting away mathematically.
You've deduced exactly what the chart is showing. That is the Neptune inversion. The sign of the residual error for the outer system literally flips, and the error for Neptune specifically crosses exactly through 0, but only if the Harmonia node is placed perfectly at 2.1437 AU.
Wow, it really is an anchor.
It acts as an independent, undeniable mathematical indicator that this specific empty chair is the structural anchor for the entire outer solar system. Without the Harmonia node, the harmonic ladder falls apart and the model fails.
It is a breathtaking intellectual picture. The geometry of a stone cross gives birth to the silver ratio, which predicts the planets to within a fraction of a percent, all balancing on a missing fulcrum defined by pi. It's a cosmic symphony.
It really is.
But, and this is the biggest but in science, a beautiful mathematical model without real-world proofs is just philosophy. The universe doesn't care if our math is pretty. The math has to be testable. How do we actually prove if this invisible grid is really out there?
This is the critical transition point. This is what elevates Gerby's paper from an intriguing mathematical exercise into a robust, falsifiable scientific hypothesis. A good theory must make predictions that can be proven false. If you can't test it, it isn't science.
So what are the tests?
Gerby outlines 2 major, highly specific ways to test the silver ratio harmonic framework.
I assume the first test is pointing our telescopes at that empty chair at 2.14 AU.
Precisely. The model absolutely demands a structural physical feature at exactly 2.14 AU. So Gerby says to the astronomical community, go look. Right now, we have access to incredibly powerful, high-precision orbital surveys.
Like what?
The European Space Agency currently operates the Gaia mission, specifically the Gaia DR3 dataset, which is mapping millions of small solar system bodies with unprecedented accuracy.
Okay, but what exactly are astronomers supposed to be looking for? If we haven't seen a planet there by now, there obviously isn't a giant globe of rock hiding from us.
No, we aren't looking for a single intact planet. The violent history of the solar system likely prevented a full planet from forming there or destroyed it if it did.
So what's left?
What we are looking for is the gravitational ghost of Harmonia. We should find a distinct gravitational clustering of asteroids at that specific distance. We might find a specific mean motion resonance, which is a region where the orbital periods of small rocks sync up with Jupiter in a stable, repetitive ratio.
Or what else?
Or we might find a noticeable, anomalous density enhancement of small rocky bodies. Basically, we are looking for the physical debris trapped at the bottom of that mathematical valley.
And if they look at the Gaia data and they scan 2.14 AU, they find absolutely nothing, just empty space and normal asteroid distribution.
Yeah, the model dies. If there is absolutely no structural significance at 2.14 AU, the silver ratio harmonic framework is falsified, period.
That is a remarkably bold claim to make in a published scientific paper. He is handing his critics the exact weapon they need to destroy his life's work. He is saying, look at 2.14 AU. If there's nothing there, I am completely wrong. You have to respect that level of scientific integrity.
I really do.
So that's the test in our own backyard. What is the second test?
The second test looks outward, far beyond our sun, exoplanets.
Oh, interesting.
If this silver ratio geometry, this convergence of gravity, resonance, and stable mathematical valleys is a universal organizing principle of physics, it shouldn't be unique to us. We should be able to point our telescopes at multi-planet, exoplanetary systems around other stars, and we should find similar silver ratio ladders.
Systems like TRAPPIST-1 or the Kepler discoveries. We should see alien solar systems spaced out by that exact same 2.414 multiplier.
Yes. The paper formalizes this test mathematically. You take a reference planet in an alien system, establish it as the baseline, apply the silver ratio algebraic functions, and you should be able to predict the orbits of the other planets in that system.
And if it doesn't work,
If we analyze well-characterized, stable multi-planet systems across the galaxy, and they systematically fail to exhibit these harmonic ladders, then this model is just a localized numerical curiosity. It would mean our solar system is just a weird, isolated freak of nature.
but if they do show those ladders, it means this geometry is a fundamental property of how planetary systems form everywhere in the universe.
Exactly.
Which brings up a really important nuance that we need to clarify. I don't want anyone walking away thinking this paper just invented a new law of physics. The paper explicitly states that this is a phenomenological model. Can you unpack that word for a layperson?
It is a crucial distinction. A phenomenological model describes what is happening within a system with incredible predictive accuracy, but it doesn't propose a new fundamental physical force to explain why it's happening.
Give me an example of that.
A great historical example is early thermodynamics. In the 19th century, scientists developed elegant mathematical equations that perfectly described how gases expanded when heated. Those equations worked flawlessly.
But they didn't know why.
Right. Those scientists had no idea that gases were actually made of microscopic atoms violently bouncing off each other. The equations were phenomenological. They mapped the macroscopic phenomenon perfectly without explaining the microscopic cause.
They knew the shape of the map, but not what the grounds was made of.
Exactly. Gerby is very clear on this point. He is not proposing a new silver ratio force. There is no magical geometric gravity string pulling the planets into place. He fully accepts standard astrophysics.
So it works with existing physics.
Yes. He is suggesting that the known physical forces, accretion, chaotic migration, resonance, gravitational scattering, ultimately push planets into this silver ratio geometry because that geometry represents a state of lowest variance. It is the most highly stable, energy-efficient configuration that the laws of physics allow.
It's less like discovering a brand new hidden law of physics, and more like discovering the universe's favorite resting position. The chaotic pinball machine of the early solar system bounces the balls around violently for 1 billion years, but eventually the balls have to drop into specific, geometrically defined slots to rest.
That is a perfect synthesis of the idea. The silver ratio isn't the physical force moving the planets. It is the compact mathematical encoding of the net outcome of billions of years of complex, coupled gravitational interactions. It is the signature of stability.
Which is still incredibly profound. The fact that the ultimate outcome of billions of years of chaotic, violent gravity just happens to perfectly match the geometry of a 3x3 grid and a few circles, I mean, it's wild.
It really is.
And this idea of nature favoring specific quantized levels, these distinct steps on a geometric ladder where things are allowed to rest, it leads to a startling, highly speculative parallel drawn at the very end of the paper. It bridges the gap between the infinitely large and the infinitely small.
You are referring to the final section of the paper titled The Bohr Solar Correspondence. Gerby concludes his research by drawing a purely formal structural analogy between the macroscale solar system as mapped by the SRHF and the microscale Bohr model of the atom.
Let's do a quick refresher on the Bohr model. Early 20th century, Niels Bohr is trying to figure out how atoms work. He realizes that electrons orbiting the nucleus of an atom don't behave like standard planets. They don't just orbit at any continuous distance they want.
Right. Before Bohr, classical physics assumed an electron could sit at any distance from the nucleus, just slowly spiraling inward. But Bohr realized that the microscopic quantum world is strictly quantized. Electrons are locked into discrete, specific energy levels.
Like steps on a staircase.
Exactly. They can exist in orbit level 1, or they can exist in orbit level 2, but it is physically impossible for them to exist in orbit 1.5. They don't slide smoothly between orbits. They jump from step to step on a quantum ladder.
And what Gerby is pointing out, there's an amazing visual in the paper comparing the two models side by side, is that the solar system seems to behave in a remarkably similar way. Planets don't just orbit at random continuous distances. Thanks to resonant attractors and the silver ratio, they appear to be locked into discrete, quantized orbital radii.
Now, we must be incredibly careful here, and Gerby is very careful in the text. This correspondence does not mean that quantum mechanics operates on planetary scales.
Let's be very clear about that.
Right. There is no such thing as a planetary Planck's constant. The planets are not quantum wave particles jumping instantaneously between orbits.
Right. Jupiter is not going to suddenly quantum tunnel its way past Saturn. We are dealing with classical gravity, not quantum electrodynamics.
Exactly. What the paper is highlighting is a profound structural analogy. In the atomic scale, you have quantum integer numbers determining the allowed orbits for electrons, governed by stationary bound states of energy.
And in the planetary scale,
You have integer indices in the silver ratio sequence determining the allowed orbits for planets, governed by phenomenologically long-lived resonant gravitational configurations. While the underlying physical mechanisms are completely wildly different, the resulting mathematical architecture is eerily identical.
it suggests that across vastly different scales of reality, the macrocosm of a solar system spanning billions of miles, and the microcosm of a single atom measured in nanometers, nature utilizes the exact same discrete mathematical patterns to organize matter efficiently.
It's a poetic symmetry.
As above, so below. The universe simply likes quantized steps. It abhors the methy spaces in between.
It raises profound philosophical and physical questions about underlying organizing principles. Why do these specific algebraic forms recur across different contexts? Gerby is isolating this geometric pattern and offering it up to the broader scientific community.
Saying basically, look at this structure.
Yes. He is saying, we know the math works. Now, how exactly does this macro quantization emerge from the chaos of early protoplanetary disk dynamics? It is a vital hypothesis-generating step for the future of astronomy.
Well, it has been quite an intellectual journey we've been on today. We started by looking at the messy, chaotic construction site of the solar system, assuming it was all just random noise, and we've slowly dusted off what appears to be a master blueprint.
A blueprint that's been there the whole time.
We walked through the history, moving past Johannes Kepler's flawed, beautiful Platonic solids, and seeing how the Titius-Bode law worked for a moment before collapsing in the cold, dark reaches of Neptune. And then we unpacked the silver ratio harmonic framework.
A framework derived purely from the most elementary geometry imaginable. A 3x3 grid, concentric circles, and an octagon.
The geometry of the Celtic Cross, yielding that magic multiplier, the silver ratio of 2.414. We saw how applying that quadratic field mapped the actual observed distances of all 9 major planetary bodies with a staggering precision of 0.72%.
Beating the history books by an order of magnitude, with a probability of random chance sitting at a microscopic 10 to the negative 13th.
We explored the Harmonic Basin, that deep, stable valley in the gravitational landscape that physically demands the existence of the Harmonia node. An empty chair sitting perfectly at 2.14 AU, acting as the vital fulcrum between the rocky terrestrial worlds and the outer gas giants.
A point where algebraic geometry, empirical data, and the transcendental constant of pi squared over 3 all perfectly, miraculously converge.
And we looked at how this theory lives dangerously on the edge of the sword of falsifiability. It challenges astronomers to comb through the Gaia data at 2.14 AU to find the gravitational debris of Harmonia and to look at distant alien suns to see if other worlds walk those exact same silver ratio steps.
And if we connect all of this back to you, the listener, the ultimate takeaway here is a profound reminder of how the scientific process actually works. Science is an ever-evolving, relentless process of pattern recognition.
We assume we understand the chaos of our reality. We accept the messy house until a new lens, a new mathematical framework allows us to suddenly see the underlying elegant order.
Exactly. So the next time you walk outside on a clear, dark night and look up at the stars, try to shift your perspective. Remember that you aren't just looking at random dead rocks floating aimlessly in a dark void. You might very well be looking at the interlocking gears of a perfectly tuned, mathematically quantized instrument.
I love that image. And I want to leave you with one final lingering thought to chew on. Let's go all the way back to the beginning. Let's go back to the visual origin of this entire mathematical framework.
The cross.
The geometry of the Celtic Cross, the ancient ringed cross, carved into standing stones by monks across the British Isles. They carved those stones long before the invention of the telescope, long before Isaac Newton formalized gravity, long before Kepler deduced orbital mechanics, and long before anyone knew what an exoplanet was. Is it just a sheer, uncanny, incredibly lucky coincidence that this precise geometric pattern, this specific aesthetic arrangement of squares and circles favored by ancient artisans, happens to mathematically generate the exact fractional constants that map the orbits of our solar system to an accuracy of over 99%? Or is there another, far more provocative possibility? Is it possible that the ancient builders, philosophers, and mystics who originally conceptualized and carved those Celtic crosses had somehow intuited, observed, or mathematically encoded a fundamental universal knowledge of cosmic geometry?
It's a heavy thought.
They didn't have supercomputers or orbital telemetry, but they had the night sky, and they possessed a deep, intuitive understanding of proportion, harmony, and resonance. Are we, with all our modern astrophysics, our billion-dollar space probes, and our complex supercomputer integrations, merely rediscovering a harmonic truth about the universe that ancient geometry tried to show us in standing stone over 1,000 years ago?
Have we just finally found the architect's original blueprint sitting in the attic the whole time?
Something to mull over the next time you see a pattern in the world that feels just a little too perfect. Until next time.